All right. Give this a try. Give it a try. Don't be shy. Okay. So solve Ax equals b. So I put this into a augmented matrix as I normally would. So again, you can put a line here. You can not put a line there. It's up to you. So this is just a one-step reduction. A little bit strange, but that's it. So if my variables are, let's choose my variables to just be x and y. When there's two variables, I usually just go with x and y rather than x1 and x2. I definitely don't want to do x1 and x2 because I'm already using x1 here. So anyways, my variables for these two columns will be x and y. So converting that top row back into an equation, I get this. So x is 3y plus 2. It's my only equation. So my vector of variables is like so. I get 3y plus 2, then just y. So I conclude that the solution is y 3 1 plus 2 0. Part B is to identify x0. So x0 is the general solution to Ax equals 0 in vector parametric form. Now, some things just come to mind. You don't have to take this variable and replace it with a parameter. You can. If you want to replace that with like a t, that's fine. I don't really care. You can leave it as a y, or you can put a t in there. It's up to you. And then the x1 is the constant part of this solution. Okay, C says calculate Ax0. So A, I've forgotten, what is A? 1 minus 3, negative 2, 6, times x0. I'll go with the t. Now we'll use our fancy trick here to make the t move out front. Okay, your alternative is to put the t in and then do this multiplication. I think that's unpleasant, but strictly speaking, not wrong. Beep, boop, 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 and then what do I get? Well, I do my multiplication. I get 3 times the first column plus 1 times the second column. And as I expect, I get the 0 vector. Now Ax1 is this guy times 2 0. So I get 2 times, I made it, something's gone wrong here. Negative 2. Boom. 2 times the first column plus 0 times the second column. So I get 2 minus 4. which is indeed my B from the original question. I hope. Double check. A little double checky. Where's the B? Sorry for all the zooming in and out. There we go. 2, -4. Okay. Now, some extras here. I want to think a bit more about the identity matrix. So I want to point out an important property is that when you take the identity matrix, in this case the 3x3 identity matrix, and you multiply by a vector, what do you get? Well, sometimes you just have to grind it out a few times, and then you will see the pattern. And then you never have to do all that work again. What do I get? I got X again. I came right back to where I started. So let's write that down. I3 times X does indeed equal X. So the identity kind of acts like the number 1. Sometimes I say that I3 exists in the land of matrices, and in the magical land of matrices, the identity matrix kind of plays the role of the number 1. So 1 times 10 equals 10, and similarly, identity times a vector equals that same vector. Kaboom. Okay, I've been talking about vectors for a while now, and I want to throw in a few definitions here. Now, we know what the real numbers are. Now, we're going to define R3 is to be the set of all, let's write it in English here, set of all 3-dimensional vectors. Okay, more formally, we'll use a brace to indicate that we're talking about a set here. And then we'll tell you what the elements in the set look like. Well, these are 3-dimensional vectors. The 3 entries could be different, so I put ABC. Then I put a little colon. The colon could be interpreted as such that. And the only condition here is that A, B, and C are all themselves real numbers. Okay, so in English, as I go from left to right, I can read this. So the brace says we have a set. The elements are vectors with entries A, B, C, such that this condition holds. And then I close my bracket to finish off there. Okay, so that's R3. Now Rn is the set of all n-dimensional vectors. So sometimes we don't want to specify what the dimension is. So it's the set of all n-dimensional vectors. So I don't know what I'll go A1, A2, A3. I'm not specifying, so I'll just go ... And the last one will be An. So n is some number 2 or bigger. Well, I guess as I've written this, technically it's at least 4 for n, but hopefully you get the idea. And then the only condition is that A1, A2, A3, ... all the way up to An These are all real numbers. Now, the zero vector, there's a zero vector here inside the R3, and there's also a zero vector in Rn, right? So the zero vector can take different forms. So in general, you have just a vector filled entirely with zeros. If you want to specify, let's say in R3, the zero vector is 0, 0, 0. In R2, the zero vector is just 0, 0. And this guy up here, I would say, this guy is in Rn, because I have not specified the dimension. Okay, so Rn and the zero vector, hopefully I've pinned those down a bit more carefully for you, a bit more clearly, rather. Okay. Exercise to wake you up. Calculate In times x and A times the zero vector. So A is an M by N matrix. Go, go, go. All right. Here you should hopefully be getting In x is just x. Maybe more details here. So I would go In, I would go, this is 1, 1, 1, then it's got ones all the way down the diagonal, some unspecified numbers. Now the entries in x, I'm going to call them, say, x1, x2, dot, 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 all the way down to xn. The convention is that if I leave blanks in my matrix, the convention is that those are zeros. So if I leave a blank in a matrix, which is convenient to do sometimes, you're supposed to interpret those as being zeros. So when I perform this multiplication, I get x1 times 1, dot, 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 0. These are zeros except for that. Then I get x2, 0, 1, 0, dot, 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 all the way to 0. And then so on and so forth, all the way to xn times this vector. And then what do you get? Well, you just get x1, x2, dot, 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 all the way to xn, which is my original x. Okay, to summarize, In x is always just x. Okay, A times zero vector is going to be the zero vector. So maybe I'll say it a bit more carefully. If I have A times the zero vector, if I want to talk about the zero vector in Rn, maybe I could put a little subscript here to say that, Rn okay, so I have n entries in my vector. N could be 17, n could be 26. So here I have, why don't I say the zero vector is 0n. Okay, you can write it as just zero vector, but if you want more precision, you can write the subscript there, but it's really up to you. From the context, it's usually clear what's going on. So what am I going to get? I'm going to get 0. I'm going to get the zero vector, and it'll be the zero vector with m entries, actually. You know, for example, if I had if this were A here, 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix. So M is 2, N is 3. If I multiply that by a 0 vector, well, it's going to have to be it's going to have 3 entries, right? We do not define, I'll underline this in a second, but we do not define this product. This product is not defined. We just refuse to talk about it if the number of columns here does not equal the number of entries in the vector. So I'll underline that in a second. So if your matrix vector product does not make sense, then it does not make sense. You just refuse to talk about it and say DNE. For that reason, I had to put 3 zeros here. I had no choice but to put 3 zeros there. And then when I work this out, I'm going to get 0 times 1, 4, plus 0 times 2, 5, plus 0 times 3, 6. So I get the two-dimensional 0 vector. So hopefully you see in general that A times the 0 vector is always the 0 vector. And if you want to be more precise about it, you get so I'll say it like that. Okay, my expectations are pretty light. I'm happy with this right here. Okay, these subscripts are a bit annoying to write every time. I think it's important for you to understand how matrix multiplication, when you multiply a matrix times a vector, you can change the size of the vector. Okay, you could start with a 3-dimensional vector and end up with a 2-dimensional vector like I do down here. And this is entirely governed by the M and the N. So that's important to understand. But once you understand it, you can just do simple equations like this. Okay, last thing is I'll just underline that we do not define this product. This product, we just say DNE if your product just doesn't make sense, right? If I have 1, 2, 3, 4, a 2 by 2, and then I have something like this, where I have 2 columns here, but 3 entries here, I would just stop and say DNE and make no further comment.